My name is Robert, and yeah, I'm a bioinformatics software engineer at Invitae. So we do all sorts of genetic testing to help our patients get a better sense for the underlying genetics of diseases. Today what I wanted to do is share with you a few thoughts about how you can use WebAssembly to speed up web applications. Before I get to that though, how many here have heard of WebAssembly? Wow, okay, almost the whole room. How many of you here have had the chance to use WebAssembly at work or in a side project? Okay. So I think about 6 I saw. Great, so you're at the right place. So what is WebAssembly anyway? Well, who better to ask than Siri herself? Hey Siri, what is WebAssembly? She's thinking. Shouldn't take too much longer. There it is. So WebAssembly then is a binary format for execution on the web that encodes an abstract syntax tree intended as a compilation target and features a contiguous linear memory model. Cool. Why don't we just put that definition aside? So what is WebAssembly? It's really just a new-ish programming language that runs in the browser alongside JavaScript. One of the most interesting things about WebAssembly is that you can take existing code written in other languages like C, C++, Rust, Go, and more on the way, and compile these programs to WebAssembly and run them essentially directly in the browser. This is not something that we've traditionally really been able to do well, and WebAssembly can enable that. So far, WebAssembly has been used to port games to the browser. It's been used to port entire desktop applications to the browser. It's even been used to port data science tools written in Python to the browser. Today, the case study I wanted to focus on was some of the work that I've been doing on building web applications to help us evaluate the quality of DNA sequencing data. Now, for any of this to make any sense, here's a very brief intro to DNA sequencing. So, DNA sequencing is essentially the act of taking a molecule of DNA and reading off the nucleotides, or the letters that make up the DNA, the A's, C's, T's, and G's. Unfortunately, the technology we have today doesn't allow us to just read the whole thing in one shot, and so instead we have to cut it up into small fragments and then give it to a sequencing instrument, which will give us, as an output, a file called a FASTQ file. And this file will have information about the sequence in those DNA fragments and some information about the quality of those fragments. So the goal today is to take this FASTQ file as an input and let the scientists get an interactive view into the quality of their data. So how do we do that? Well, the question is, how do we build any data analysis web tool? Typically, you'll have a data analysis portion. So this is where you'll do all the compute heavy stuff. And you'll have a data exploration portion where you'll let your users interactively explore their data. Traditionally, we've mapped this to the physical world by just doing the analysis on the server and doing the interactive exploration in the browser, which makes perfect sense. But sometimes you really want to be able to do analysis in the browser. You don't want to always have to go back to the network. So you want to make your app more responsive, and so you can use JavaScript for that. But there are a few issues. Namely, it typically will be a lot slower than running your code on the server. The other issue is that if your code is written in a different language, you're going to have to rewrite it to JavaScript, which, trust me, is not a fun exercise. The other issue is maintaining responsiveness, right? So any time you find yourself doing analysis in the browser, you're going to face a slow UI. So essentially what we're suggesting is, well, you can leverage WebAssembly to take some of these things into account. For example, as we'll see later, WebAssembly can help in some cases with speed. It most certainly can help with portability. So a lot of the tools in genomics, for example, are written in C and C++, making them perfect candidates for WebAssembly. Lastly, to maintain responsiveness, we're going to leverage a technology that was mentioned a bit earlier called web workers to allow us to run the WebAssembly in a separate thread and not have to essentially crash the user's browser or jam the scroll bar where they're trying to use it. Okay, so what is the architecture going to look like for a tool that's going to allow us to preview the quality of DNA sequencing data on the front end? So first, we started by writing a tool about a year ago called fastq.bio, and it was written in JavaScript. And this was done before we even thought about using WebAssembly. So the architecture is fairly straightforward. Given a file, you have a main controller that will parse through it, getting random chunks of the file, and then doing a bunch of string manipulations in JavaScript to calculate the metrics. How many A's do I see in a string? What's the distribution of this fragment size of the DNA, and so on. And then once you have that, you can plot the results and then keep looping through the rest of the file, and so on. What we wanted to do now, though, is replace the red box with some WebAssembly. So there's a tool called SeqTK. It's a sequencing toolkit. It allows you to get a lot of useful information about the quality of your DNA sequencing, and it's written in C. So let's take a look at what you would do to compile SeqTK to binary, right? So you just use GCC and pretty much using typical flags. But if you want to compile this to WebAssembly instead, we've been using Emscripten, which has these really useful drop-in replacements for things like GCC and G++ and make and configure, where it makes it a lot easier to compile your programs to WebAssembly. So instead of GCC, we do EMCC. Instead of outputting a binary, we want to output a .js. This will both output a .webassembly, but also a .javascript file that will initialize the WebAssembly for us, so we don't even have to think about that. The other thing I want to point out is we're including a file system. What on earth would you want to do with a file system in the browser? Well, the way SeqTK was written was with files in mind. And so to call it, you just call SeqTK, fastqcheck, and the name of the file. I don't want to have to rewrite SeqTK to handle strings as input instead of files. And so we could leverage what Emscripten gives us for free to get this virtual file system where I can take some sequencing data, mount it to a virtual file system in the browser, in memory, and then just run the command almost very much the same as I would on the command line. So the architecture looks something like this. We just replaced the red box with another red box. But to make it a little more interesting, we're going to be using web workers. So we're going to have a controller that's going to be in charge of creating and communicating with the web worker. So one of the issues with web workers is you can't just say, okay, execute this code now. You need to communicate by message passing. So we have an API that essentially takes in messages like, I want to execute a C function from my WebAssembly, or I want to mount a file to the virtual file system. I want to sample randomly through the file, and so on. So once you have that, the web worker will return a JavaScript promise, and once that resolves, you can plot the results and be on your merry way. So let's measure performance. The first way we'll measure performance is by eye, which is always informative. On the left side, I'm going to show you a screencast of using fastq.bio in the original JavaScript version, and on the right, the WebAssembly version. So we go to the website, we choose a file, and you can see they're both off to the races. If I pause it here, you'll see that the WebAssembly has gone through over 25,000 reads, whereas the JavaScript is still struggling to get through 3,000. So clearly it's faster, it feels snappier, and it updates much better. But let's actually quantify that. The way we're going to quantify that is essentially with the metric of how many lines in the file can you process in any 1 second. In our original JavaScript version, we could do about 1,000 per second. But when we took our SeqTK program, compiled it from C to WebAssembly, and then started loading it into a web worker and doing the analysis, now we're talking about a 9x speedup out of the box. And obviously you need to first wrangle your way through getting WebAssembly working, but once you do that, you get this 9x speedup, and we didn't have to modify the original C file. But what if we did? So one of the things we noticed was that SeqTK was outputting a lot of useful metrics, but that we weren't actually plotting. So we figured, okay, let's go into the code and literally comment out printf statements that we didn't need and recompile it to WebAssembly. Just doing that reduces the amount of communication that happened between the JavaScript and the WebAssembly. So now we're looking at about 13x. The other thing that we then did, there's more, yes, is to get those metrics, we had to call 2 different functions within SeqTK. So what this meant is you would sample a chunk of data from the file and then run one function on the file and then run another function on the file, meaning you would read the same chunk of file twice. So that's wasteful. So we went into the C code, wrangled those 2 functions together. It's a little messy because one of them outputs a tab-separated value output of like 5 columns, whereas the other is 2 columns. But anyway, you can make it work if you just add some extra wrangling on the JavaScript side. And it's a little messy, but it's definitely worth it because we were able to see over 20x speed up with that. Now, before I go any further, time for caveats. So this speed up is not generalizable to all tools. I don't want you coming out of this room thinking, I am going to use WebAssembly and I'm going to get a 20x speed up. So no angry tweets at me, please. Keep in mind that there are certain categories of problems that are very well suited for WebAssembly and others that are not. Shocking, I know. The other caveat to keep in mind is the baseline that we're comparing to is an application that we had initially built in JavaScript and did not really try to optimize. And I think that actually illustrates the whole point of WebAssembly is that we didn't have to waste time trying to optimize a tool that we had rewritten in JavaScript in the first place. WebAssembly allowed us, most importantly, the portability of taking an existing tool that the scientific community uses, knows, and has been tested extensively, and reuse it in the browser, and in doing so, getting speedups that are pretty good. So we've talked about one specific use case. There are a lot more use cases when WebAssembly is nice to use. One of the bigger ones is graphics. So anytime you're porting games or desktop applications to the web, WebAssembly can be a good tool to use. For example, I found somebody had rewritten Pong in C++ for some reason. And so I took that, compiled it to WebAssembly, and here is Pong running in Firefox. It's great. Did I say Pong? Pac-Man, yes. Much, much better than Pong. I'm so sorry. Rookie mistake. I'm a millennial, what can I say? Okay, data tools. I showed a few pictures of how you can use WebAssembly for image processing. And if you had asked me a few years ago, should I build a photo editor in the browser? Of course not. But it's becoming more and more a reality to be able to do these things. Obviously, we also talked about data analysis tools like FastQBio, where you can do some data analysis in the front end. Another cool application is if you have a cloud platform that requires your users to upload massive amounts of data, so like, I'm going to go to my favorite example, which is genomics. If you ask your users to upload sequencing data and you want to warn them about bad data quality ahead of time so they don't have to wait 10 hours before they realize that what they uploaded is actually not that great. That can be really useful. Now, of course, you could do that already in JavaScript, but in fields like genomics where a lot of the file formats are in binary and there are tools that are already written in C to parse those files, there's really no need to re-implement those from scratch. One area that I find is underutilizing WebAssembly is educational tools, specifically building playgrounds for command line utilities. To demonstrate that, I took the JQ source. How many of you are familiar with JQ? Okay, about like 1/5 or so. So JQ is an amazing command line tool for wrangling JSON strings on the command line. So you can modify JSON, append to it, wrangle it. And it's written in C. So of course, I compiled it to WebAssembly. And here it is, running JQ in the browser. And you can interactively make your queries. This is my input JSON. This is where the output shows up. And it's blazing fast once the page loads because it's all running in the browser. Now, there are other tools like this that will let you play with JQ, but they're typically implemented as server-side tools. So they will send the request to the server, evaluate it on the server, and then return the answer back. So this is nice because, well, first, I don't have to worry about somebody hacking the website and mining Bitcoins, since it's all in the browser. The other thing is just convenience. This site is literally hosted as just static files on Google Cloud Storage, so it's super easy. Now, this wouldn't be complete if I didn't tell you what not to use WebAssembly. And these are just examples in my own experience. I'm sure there's a plethora of other scenarios where you should not. I found that if you find yourself communicating a lot back and forth between the JavaScript and the WebAssembly, like we've seen when I commented out some of those lines and got a big speed up, you're going to see a lot of performance issues there, to the point where using WebAssembly might hurt you, right? So that's a real possibility. If you find yourself analyzing very large files all at once, so one example is if you ask users to upload a matrix of data and you want to calculate the pairwise distance between every row, you need to look at all the data. Probably not a good thing to do in the browser. This one is particularly important in genomics, where we have a lot of reference files that we need to load in memory, like the human genome reference. And these are typically gigs and gigs of size. So if you find yourself doing that, don't. One reason being that WebAssembly is 32-bit addressable, so you can't go beyond 4 gigabytes of RAM yet. But even if you could, the idea of loading more than 4 gigs of RAM on your user's computer seems a little odd. So yeah. So to summarize, 2 things we talked about. One was how in our use case we were able to leverage WebAssembly to speed up our web applications. We saw how we could use web workers to enhance the responsiveness of the app so that it doesn't bring the browser to a halt. And with that, I do want to mention that if you're interested in learning more about WebAssembly and how to get started using it, or how to use it in your web apps, or how to compile Pong and Pac-Man, then check it out at levelupwasm.com. And with that, I want to thank you very much for your attention.